Welcome to this short introduction to container orchestration. My name is Michelangelo Valsecchi and I'm Head of Product Research and Development at Visualise Info. Computing clusters are the basis of most high-performance and high-availability modern applications. Think, for example, of all social networks, asset managers, and most prominent websites and platforms, from finance to marketing to creative spaces. Managing clusters has historically been very complex, especially coordinating all the parties involved in procuring and maintaining the infrastructure. For example, if the operation teams noticed that the cluster would receive less traffic during the night and wanted to shut off some machines to save some money, they would have to go through the on-site maintenance team, which would then have to manually reduce the size of the cluster. Another example is the procurement team getting a good deal or more powerful hardware that is different from the one currently in use. Integrating the new machines would require building and migrating to a new cluster, all while coordinating with and possibly blocking development. It is no surprise that these problems, already complex to manage with a single geographically limited cluster, would explode in complexity as clusters expand to multiple time zones and regions worldwide. Container orchestration addresses all these issues by segmenting responsibilities into independent subunits and providing a clear and stable interface between them. All teams interact only with the cluster's central managing unit, also known as the orchestrator, requesting changes to suit their needs and letting the cluster itself coordinate resources. All applications run inside platform-agnostic containers managed by the cluster as stateless units, allocated according to resource availability with health metrics continuously monitored. The key is to separate the cluster into a physical cluster and a logical cluster, which are two opposite sides of the same coin, with the orchestrator serving as the glue in between. Notably, the teams working with the logical side of the cluster, like development, do not need to know the physical layout backing it, and applications should not rely on the existence of specific machines, but should let the orchestrator manage each of their components. Similarly, physical side teams do not need to know what is running on the hardware they control, as the cluster will manage application reallocation based on infrastructure changes, such as freeing up nodes to be taken offline or expanding to new machines as they become available. For example, on-site maintenance can request that the cluster orchestrator isolate and remove nodes from the cluster at any time without interrupting the development team or the applications running on it. Similarly, developers can deploy applications without knowing the cluster architecture or specify the exact machine on which to run the code, knowing that the orchestrator will assign resources most optimally. And lastly, if part of the cluster goes offline for any reason, the orchestrator automatically reallocates all missing applications onto the remaining nodes with minimal to no disruptions. To illustrate how container orchestration is used in practice, let's consider an overview of a subsystem taken from Visualise Info's IoT product, where IoT data is collected, transformed, and then stored or served to third-party services. To achieve these, we rely on a computing cluster managed by a container orchestrator, like Kubernetes. Crucially, we do not know how many physical machines make up the cluster, and we should not care, as we only work with the logical side. However, this limitation will not limit our system capabilities. It will actually allow for far greater flexibility and performance, while at the same time reducing resource usage and operational complexity. The primary requirements of the system are flexibility. It should accommodate any input source or incoming raw data and apply any user-specified transformation to it. Performance. There should be very minimal latency between receiving raw data and sending out the transformed output. Resilience. The system should automatically respond to errors and external disruptions without overcommitting resources. And lastly, scalability, as being able to handle millions of concurrent sources and adapt usage patterns over time, reducing resource usage during quiet times or recruiting more machines during peak loads. The first requirement, flexibility, can easily be satisfied by the user interface itself. A good UI allows users to specify transformation flows through an intuitive graph-based model, similar to other familiar products like Node-RED. The visual graph is then exported into a common portable representation, like JSON, detailing the sets of nodes and edges that model the data flow. The flow can then be loaded into an application that builds an in-memory copy of the graph and listens for update from the specified sources. The backend then propagates the updates through the graph and forwards them to the user-defined destinations. Being smart about implementation, for example using high-performance languages like Rust, can yield a fast and efficient binary that already satisfies the second performance requirement. To achieve the last two objectives instead, we need the guarantees provided by a container orchestration platform like Kubernetes. However, just as a car dealership deals only with vehicles and not their components, Kubernetes' most minor units are not binary applications, but containers, also called pods. First, we need to wrap our binary application in a Docker container. Once containerized, the application can be deployed on a cluster and left for the orchestrator to manage. The orchestrator will guarantee our third requirement, resilience, by scheduling the container on the most appropriate computing node, monitoring the container's live signals, and restarting the application in case of errors. And lastly, moving the container to a different node if the original one becomes unavailable. The cluster then continuously monitors the container's vitals, such as CPU and memory usage. This enables us to take advantage of the orchestrator's replication functionalities and satisfy the fourth requirement of scalability, deploying an autoscaler or a custom operator. An autoscaler is software that lives in the cluster control plane and monitors the container resource usage live. When usage rises above a threshold, the autoscaler automatically creates new clones of the application container and distributes the load among them. Similarly, when usage falls below the threshold, the other containers are deleted to reduce consumption. Once again, the orchestrator manages the newly created resources and seamlessly deploys them across the cluster to optimize physical resource usage. The process is seamless from a client, developer, and operational point of view, as the cluster autonomously manages everything internally. In summary, the key takeaway is the duality of the cluster as two separate but cohesive units, a logical and a physical one, kept in sync by the orchestrator. If you wish to find out how high-performance IoT data processing could transform your business processes, reducing costs and increasing productivity without ballooning your IT infrastructure, then contact us at Visualise Info or visit our website.